So in this video, I'd like to discuss the topic of frequency response. So as we know, any voltage, either input or output, can be expressed as the following. So some constant coefficient multiplied by sinusoidal function. Please note that I could as well choose sine function. It does not matter. But we cannot choose, for example, a tangent omega t. Why? Because AC voltage naturally has a sinusoidal shape like this. So the properties of this kind of function are usually gain, frequency, and network function. So the first one is gain. Gain is simply, let's say, gain tells us whether the signal amplifies or reduces. If I say that gain is, let's say, letter G, G can be both positive and negative. So in a case if it's positive, it means that your signal is amplified. In case if it's negative, it means that the signal is reduced. So let's say we have V input equal to A multiplied by cosine omega t and V output equal to B multiplied by cosine Vt plus, for example, theta. Then the gain is equal to B over A. As simple as that. Another important point is phase shift. So phase shift is equal to output angle minus input angle. Network function would combine these two concepts into one. So we denote a network function using letter H. So the gain that we have seen on the previous slide was B over A. And the phase, let's say angle theta. So here gain is nothing else but the absolute, and phase shift is just the angle of our network function. You usually encounter in some exercises and problems the following representation. So usually they will provide you with something like this, where Z is a 0 and P is a pole. So let's try solving an example. We see that our network function is given using this formula, and we're asked to find inductance L. Here we see two circuits. Please pay attention that this is essentially one circuit but represented in different domains. So this is a time domain and this is a frequency domain. So the problem is quite simple, and if we use, let's say, a Kirchhoff's law and take a current that flows in this loop, then we may get that V input is equal to 8I plus 2I plus, we express in this case the inductance using GVL. So this is a imaginary number. This is our omega, and this is our inductance multiplied by current. In that case, our current can be expressed as V input over 10 plus G omega L. We can also see that V output is equal to the voltage drop over here. So V output is equal to current that flows through this area multiplied by 2 plus G omega L. But the current that flows through this part of the circuit is the same current that we express this way. So we may rewrite our equation and we'll get the following relation of V output and V input. In that case, we can already see something very familiar. So this is, of course, nothing else but our network function, H. And since we're asked to find the unknown, the inductance L, we can now equate it to what has been given to us initially. So this is equal to 0.2 multiplied by 1 plus J omega over 5 over 1 plus J omega over 25. For these two sides to be equal, we have to get out the 2 and 10. Now everything becomes extremely simple. It's just pure arithmetic. We may simply take one of the values, let's say L over 2, and equate it to 1 over 5. As well as we can take L over 10 and equate it to 1 over 25. Please notice that these two give the same L, which is essentially equal to 2 over 5. So we found what we wanted, and the answer is 2 over 5.